I'm really excited to be welcoming Neil to present the last seminar. Neil was a master's student of mine at the University of Michigan, and he's one of these people who showed up and said, "Hey, I want to work on big animals." I don't work on big animals. And
that's still how I go about just interacting with everybody.
Yeah, it's like, I'm going to do what I want to do, and just don't get in my way, is kind of the way it felt. And he said, and he went and talked to the DNR and said, "Hey, they got data on bears. Can I do bears?" I said, "Oh, okay." So, and spatial modeling, so I was like, okay, I can hang with this. And he says, and they're going to give me money. So he went out and got his money, and he said, I want to do this Bayesian modeling stuff. And I don't do that. And he sort of went and found somebody to teach him Bayesian modeling, and did a great study of bear distributions in northern Michigan and interaction with people, and got it published, and then went off to Michigan State to do his PhD with Jack Liu. Again, working on big animals in tigers in Nepal and China, maybe? Nepal, yeah. And then decided he wanted to do a postdoc with Cy Levin, and got funding from Session to do that. And then just kind of one of these people, well, at least my experience as a master's student, just kind of didn't need much help, and that was pretty wonderful to see, and wonderful to see what you've accomplished so far in your career, and look forward to seeing what you accomplish next as you move on to a position that opened up at the University of Michigan last year. And he has just informed us that he's taken that position at the University of Michigan. And so that's pretty exciting too.
Pretty big.
It's an empty hole, whatever it is. So congratulations on that, and I look forward to hearing about you.
Thank you, Dr. Brown. Thanks, everybody. Thanks for being here. It's a pleasure to be here. This is my first time on campus. It's a beautiful campus. It's been a lot of fun. And if someone had told me that one day I would be giving a guest talk underneath the head of a dead elk, I would have said, if only I would be so lucky. Here I am. So it feels like this might be my peak. I peaked. This is it. So I'm going to talk to you a little bit today about work that my research group is doing to understand wildlife ecology in a brighter and a louder world. And I'm also going to preface that my throat has really been scratchy, so I'll be doing a lot of this. And I apologize about that. Before I get started, I'd like to acknowledge a few people, because I have a pretty tremendous team that's been helping me on this work. And first and foremost, I want to highlight the three co-Is on this project: Jesse Barber at Boise State, Clint Francis at Cal Poly, and David Stoner at Utah State, who have been helping me to develop this work and understand the implications and what it means for ecology and conservation. Also, very importantly, I want to give a shout out to my postdoc in my lab right now, Mark Dittmer, who's been doing a lot of the analyses and data wrangling that I'm going to be presenting and talk to you about today. So I'm very thankful for his help. Also, of course, I want to be supportive of the funding for this work. We have a grant from the NASA Applied Sciences Division, and the Applied Sciences Division is actually interested more on the applied components of science, and in particular decision support tools, instead of the more basic element of science. But today I'll be talking about some of the more basic components of the research, because I find that very interesting. And also funding from the National Park Service, because they're our partners on this work and interested in using this kind of information to target mitigation measures for the park units around the country. So when I'm talking about a brighter and louder world, I'm referring to artificial nightlight and human-made noise. And the reason that I'm going to talk about amylin is that it is an extremely pervasive and a spreading form of stimuli and pollutant. For example, one study estimates that half of the land in the contiguous US is exposed to night lighting. And another study found that globally, the amount of land that is exposed to night lighting is increasing by about 6% per year. So it's rapidly growing around the world. And the same goes for human-made noise. One estimate puts 90% of the land area in the US experiencing elevated sound levels from anthropogenic noise. from things like road networks, cities, industry, residential areas, various forms of human activities around the country. 83% of the US area is within 1 kilometer of a road of some kind. Much of the noise is from road networks. And this is not just in urban areas. A study last year in Science found that elevated sound levels were encroaching even into the protected area network and encroaching onto critical habitats in that protected area network. So in my opinion, we have a pervasive form of a pollutant. It's something that we don't know very much about. Keep in mind that the natural light and sound regimes for wildlife have been consistent for extremely long periods of time. Sun goes up, sun goes down. Sun goes up, sun goes down. This has been a stable evolutionary force that has, organized a lot of different patterns and processes in ecosystems. So in a relatively short period of time, largely due to human activities, we have radically disrupted these evolutionarily stable regimes of light and sound. So not surprisingly, in the last few years, there have been a number of studies that are starting to document the detrimental effects of these stimuli on a number of fitness-related behaviors for wildlife, including migration, the timing of reproduction, interspecific communication, prey detection, predator avoidance. Most of these studies have been experimental, or they've been done in laboratory settings. What we're still missing is work that examines the effects of nightlight and noise on wildlife habitat use and connectivity at large spatial scales. My background and interest is in spatial ecology, and it struck me as a really interesting and useful line of inquiry to start extending what we know from the laboratory and experimental settings. Because we don't know very much about that, conservation planners lack information to help them target where they should focus their mitigation efforts, why they should focus them, or what species they should focus on, because the information that we have is not at the policy relevant scale. So my colleagues and I worked on this NASA grant, and were awarded this grant to work on this, addressing these two knowledge gaps. And to do that, we're going to try to link together what we do know about the micro level, in this case, animal traits and the relationships between functional traits, morphological traits, life history traits, and the sensitivities of those animals because of those traits to night light and noise. So we're scouring the literature, and we've also administered an expert survey to try to collect some information on what are these traits and what are their role in influencing animal sensitivity. We've also compiled a huge amount of empirical data, both remotely sensed. Primarily, I'm going to focus on NASA's VIIRS day-night band sensor, which was launched in 2012 and collects nightlight readings around the world every single day. The sensitivity of that satellite is extremely high, but it comes at a cost. The spatial resolution of that imagery is about 750 meters. So we'll talk a little bit about what that might mean for the results coming up later. The Park Service has also created a sound map for the whole contiguous US. And then we also have a lot of field data, primarily from GPS-collared animals around the country and from citizen science data sets from public repositories like GBIF, NestWatch, FeederWatch. So we're trying to integrate all of these together using a number of different analytical approaches like step selection functions, resource selection functions, distribution models, and vulnerability mapping to develop a geospatial framework for our partners in the Park Service to help them figure out where to guide and target their mitigation measures. Today, I'm going to be focusing on one facet of this overall work. But before I do that, I wanted to give you a sense of the spatial heterogeneity and distribution of nightlight and noise. So again, the nightlight is coming from a NASA sensor, and the noise that we're showing on this map is a modeled outcome created by empirical data collected in the field by Park Service employees. So they've essentially modeled the distribution of sound at a 270-meter resolution across the whole contiguous US. And this is a bivariate choropleth map. So the maroon areas are where we have both of those stimuli together. And you can see, obviously, this matches up really closely with road networks, urban areas, most of the eastern half of the US, is covered in maroon because they have a lot of urban areas. But there's also some interesting disparities in where we have light and sound. So you'll notice that in the middle portion of the US, there tends to be some elevated sound levels, but not so much light. Not exactly sure what that is, but it could be related to agriculture. So there might be high levels or slightly elevated levels of sound over natural background sound because of the intensity of agriculture in the area. Could also be related to the growth of exploration of natural gas in the area, so related to some of the industry in the area, but it's unclear exactly what's happening there. And then in the west, it's the reverse. We have some slightly elevated levels of light, but we have virtually no sound in some of these vast deserts. And part of that could be the fact that there is so sparsely vegetated that light can travel much longer distances, so that Las Vegas beacon is basically covering huge portions of the desert. At any rate, there's a lot of interesting heterogeneity in these two forms of stimuli. Today I'm going to talk about cougar deer ecology in the southwest region and how that ecology relates to nightlife in particular. So for today's presentation, I'm going to focus on some work that we're doing to try to understand the effect of nightlight on predation risk of deer from cougars. Talk about how nightlight is affecting animal activity patterns. And then finally, talk a little bit about some future work and conclusions. And why I was especially excited to talk to you all about this work, because it's in a relatively preliminary phase, is I'm really keen to get your input and feedback on some of the results that we're seeing. We're at this sort of midpoint in the project, we're starting to get some results, and now we're trying to interpret what these results mean. And I think there's a lot of different ways that we could go with these results, and I'm interested to hear what you might think about those. Cougars and mule deer in the Great Basin and Colorado Plateau. This is where we have our data, and I'm going to focus on these two ecoregions. It's quite interesting for this particular question. These two ecoregions are some of the most sparsely populated regions in the whole U.S. As such, they have very low levels of nightlight and noise, particularly when we look at with respect to the eastern portion of the United States. However, the Southwest has relatively mild climate, strong economies, and a lot of access to outdoor recreation. So the Southwest is the fastest growing region in the US. A lot of mid-sized cities are growing very, very quickly. So state and federal agencies are very concerned about their wildlife and how this growth is going to impact those animals. And so they've invested tremendous amounts of effort and money to map habitat use for their large mammals and migratory routes for the mammals in the face of this land use change. So we've gotten in touch with those agencies and we said, can we use your data, and we'll look at this question of whether or not nightlight might be something of interest when we start modeling habitat use, migration, connectivity, and so forth. So from that, we've compiled a fairly large data set of GPS individuals for both cougars and mule deer in the southwest region. We now have GPS collar data for 110 individual cougars, comprising over 200,000 locations. We also have over 460 GPS collared deer, over 1 million locations of deer in this region. We also have over 1,600 kill sites. These are documented locations where deer were killed by cougars throughout this area. So this is the data that we're going to use to try to understand predation risk, because we know that they were predated on. This is the distribution of the data across the Great Basin and Colorado Plateau. So the white boxes are places where we have either mule deer data or data from cougars or both. And in the background is an image showing the nightlight in this area. So you can see the cool blue colors, it's very, very low levels of light, so the deep deserts of Nevada. And as you move southeast, you start seeing increasing levels of light. So essentially we have a fairly good gradient of light across this whole region. And in particular, when you add cities like Salt Lake, Reno, and Vegas, you get some really strong hotspots of light. And we have data for both of these species in all of those locations. So we have very, very rich data, and to give you a sense of the richness of this data, this is the NASA imagery, and the brightness of each pixel is equivalent to the nightlight level. So wider pixel, more nightlight. This is in the southwest portion of Salt Lake, so it's a residential area. And we'll see a video here of two mountain lions, GPS colored mountain lions, shown as the bus brown, and two mule deer in green. And you can just see that there's a lot of data here on their movement and the way they're navigating around these well-lit areas. They're not leaving these areas. They're hugging this residential area and these well-lit zones. Deer are concentrating in some areas and feeding, and cougars are moving around and establishing territories. So really terrific data set that we're working with and trying to understand the extent to which these animals are navigating around this new kind of stimulus. Interesting side note, if you look over here, this is the accumulated values of nightlight based on the locations of deer and cougars, and you can tell that the two deer are selecting for slightly more lit cells than the mountain lions are. Keep that in the back of your head as we move forward. Okay, so we have all this data, and my research group and I sat down and we thought to ourselves, okay, let's be good scientists and develop a priori hypotheses first, or we do all the analysis and then fill in the hypotheses later. And we said, okay, I think we have two broad categories of hypotheses to help us understand how cougar deer ecology is related to nightlight. The first is the human shield hypothesis. We call it predator shield. In this case, we hypothesize that deer are actively using some of these places with nightlight as a way to buffer against the predation from cougars. Cougars are famously shy and elusive, and so deer are going to use these as places where they can have some refuge from the predation risk from cougars. On the other hand, you can envision that there could be somewhat of a predator buffet. Cougars aren't dumb. They're very adaptable, behaviorally flexible, and so they might be able to exploit some of these areas and take advantage of deer despite the light. They're a visual predator, and they can use that light to help them to be most successful in their hunt. Two broad categories of hypotheses. Of course, it's going to be much more nuanced than that. But moving down a stage, how can we test this with the data that we have? If we have a predator shield, and again, these are just some of our thoughts, so I very much welcome alternative ideas of constructing these hypotheses or relationships that we might see. But if we have a predator shield, then we might expect to see deer move slower in a more tortuous way. This is more zigzaggy. And select for higher levels of vegetation greenness in areas with high nightlight. So they found these areas with high nightlight, they've got their refuge, and they're going to just settle down and feed and use those areas. We should also expect to see that they're going to be indifferent to predation risk in areas of high nightlight because they're not worried about it. And lastly, we should expect to see that their activity patterns will lengthen in areas of high nightlight, or they won't align very closely with cougar activity patterns. Again, because they're sort of decoupled from what cougars are doing. They're just exploiting these areas as a way to get away from cougars. From cougars, we should expect to see that they are not located anywhere near nightlight, their kill sites won't be anywhere near nightlight, and their activity patterns will really only align well with deer in places that have low light levels, because they're essentially avoiding entirely anything with high nightlight. This is all artificial human-made nightlight. In contrast, if we're looking at a predator buffet, we should expect to see very little difference between habitat selection of urban deer versus wildland deer. The activity might shorten in the brighter areas because they are exposed to greater predation, so they're going to use those areas for a relatively short period of time. For cougars, we should expect to see them actually selecting for those lit areas because, again, it's a buffet. They're going to have more slow, concentrated movements in those areas of high nightlight as they're spending time trying to hunt and track down their prey. The kill sites will tend to be in areas of high nightlight, and there should be a very large difference in the selection patterns and activity patterns between the urban cougars and the wildland cougars. So this is how we envision this playing out with our data. The way we're going to address these hypotheses, we've got a number of different analyses. I'm only going to focus on two of these for today's talk. The first I'm going to talk about is a resource selection function analysis that we're doing for those kill sites to help us understand predation risk across these landscapes and the role that light might have in influencing predation risk. To start to do that, we want to classify our study sites by the level of exposure to nightlife. So we have 22 different study sites that we have these data for. And I apologize that the font is pretty small, but on the x-axis are our study sites, all 22 of them. And the y-axis is the exposure to nightlight in those areas. And we used a K-means clustering to see if there were some natural breaks in the level of light in our different sites. And there are. So 17 of them have very, very low nightlight levels. And these are places deep in the wildlands, some of which are national parks, and some of them are just very far away from any kind of human activity or presence whatsoever. And green are our medium sites, and these include some mid-sized cities like Reno and Flagstaff. So there's a concentrated urban area creating a sky glow around it. And then all the way on the right, for which we have a third of our kill sites occurring, is around Salt Lake City. This is a very, very bright area, demonstrably brighter than all of our other study sites. So it gets its own special category. You're welcome, Salt Lake. You're very bright. Okay, so for the remaining few slides, we're going to be talking about these different study sites by these different groups that they're in based on the exposure to nightlight. So for the resource selection function, in this case, we're going to be developing one for, let's say, Flagstaff. This is a map of the nightlights, and you can see, obviously, the nightlight is highest around the urban area, and it drops off very quickly as you leave. Flagstaff is fairly small. Then we have our kill site locations shown in green, and we want to compare those, the characteristics at those pixels for kill sites versus random sites, which are shown here in red, to see if there's some kind of statistical difference between where the actual kill sites were and where you would expect random locations to be. Okay, so looking at some results, I find these really fascinating, and I think we're seeing something really interesting about nightlight. On the x-axis, we have that mean light exposure. So again, the color code is for those three different categories. The blue is solely Salt Lake. Green are those four mid-sized or medium forms of nightlight exposure, and red is very, very dark areas. Right away, we see in this kill site resource selection function, kill sites in Salt Lake are negatively related to the actual light levels at those locations. In other words, very bright area, the Cougars are killing deer in the darkest locations of that very bright area. But we see the reverse in a place like Reno. Moderate levels of light, and Cougars are killing deer in places with higher nightlight. I'm not entirely sure why that is, but I have some thoughts. Aaron, help give some thoughts on it as well. And we see a non-significant relationship in the low light level areas, which makes sense because the light levels are so low to begin with, it would be surprising for there to be a statistical relationship. But this disparity between the high light exposed site of Salt Lake and everything else continues. Here we're looking at distance to forest edge. So biology of cougars suggests that they should be staying really close to the edge of forest or an ambush predator. We see that in the low and the medium level sites. But in Salt Lake, they're actually killing deer in places farther away from the forest edge. When we look at terrain roughness, again, we see a very different relationship in Salt Lake. The biology and ecology of cougars suggests that they should be selecting for kill sites that are going to be in more rough terrain. That's cougar ecology. They like to ambush and hunt from topographically complex areas. In Salt Lake, on the other hand, they're killing deer in places that are flat. There's very little terrain roughness. So something very different is happening in terms of the predation risk in Salt Lake versus everywhere else. And so this is simply to show the overall model results. So in red, we have the negative relationships. In green, there are positive relationships. And I definitely don't want you to try to decipher all of this because there's a lot on there. There was just two things I wanted to point out. First is, across all three of these, predation risk varies considerably. And I think light has a lot to do with the changing risk landscapes in these different levels of light exposure. And in particular, when we look at the Salt Lake place, that nightlight has the strongest effect on the likelihood of predation. Something about nightlight around Salt Lake is really driving where cougars are killing deer. We can mush this all together and start mapping the likelihood of predation risk for all 22 of our sites. So here we're looking at the map predation risk for Salt Lake City. On the left is the land cover data set, so red is the urban area and green is the forested area. and this is the mapped likelihood of predation. So you can see as you get into the natural forest areas of the hills, that risk goes up. And this corresponds really, really well with the actual locations of kill sites. In part, this is because this model was fit to the Salt Lake study site. This correspondence breaks down a little bit when we look at one of those 17 low light sites, because that model was built pooling all of the data for those 17 sites. So this is the predicted likelihood of predation in Capitol Reef National Park, and overlaid on it, you can barely see those green locations. Some of them match up pretty well with the predicted likelihood, and some of them are just completely off. But this is to be expected because this was a pooled analysis. So some parts are going to get well, and some parts don't well. So these predation risk layers already, I think we're getting some really interesting results in terms of the effect of nightlight. What's going on? It certainly seems like the way that cougars are killing deer, or the way that deer are trying to avoid cougars, is changing considerably with increasing levels of nightlight. And the idea moving forward is that we're going to be using that predation risk as a predictor of other attributes in terms of their selection for habitat. Now I'm going to talk about the activity analysis, and this is, we can take advantage of that really rich data from those GPS collars. And so for this analysis, we're going to group deer in low, medium, and high in a slightly different way, because now we're focusing on the individual deer and their home ranges. So to give an example of that, previously I had classified Salt Lake as the high light exposure area, but now that we're focusing on individual deer, some of the deer, their home ranges were well away from the high nightlight area. So we would actually reclassify these as a low light exposure deer, whereas this deer is really in a very high light exposed area, so that's now in a high light exposure category. So it's individuals rather than the study sites. So the question I want to answer here is, do activity length and times of day differ among the levels of nightlight? To what extent does nightlight potentially influence the changes in activity length? On the right, we have our 22 study sites, and the different colors delineate those different sites. And the orange are those study sites that we have GPS colored field here. So for some of them, we actually have those GPS colored. The model we use for this activity analysis is a generalized additive mixed model, and we're accounting for the fixed rate in our GPS collar. So sometimes they were getting fixed rates every hour, every 2 hours, every 4 hours. We've also accounted for moonlight at the time of the location, Julian date to try to account for some kind of seasonality that we might be missing, vegetation greenness that we're capturing in the NDVI metric, and the sun position at the time of that location. For example, was it nighttime, crepuscular, or daytime? And just to remind you, if it's a predator buffet, we hypothesize that we should expect to see mule deer shorten their activity pattern in those brighter areas because they will feel exposed to predation. And if it's a predator shield, we expect for those activity patterns to lengthen, potentially to be more at night, because now they no longer have to worry about avoiding cougars, but they're trying to avoid people that are more active during the day. So right away, when we start looking at the raw data for our individual deer, we see a very interesting relationship with vegetation greenness. These are our deer in these different categories. So each of these points are an individual deer. You can see really clearly that animals that are in the high nightlight group also have much higher vegetation greenness. And this is something of a linear relationship. To me, this suggests part of the reason of why they're even using some of those high nightlight areas, that the forage could be extremely high, and it's probably really consistent if it's a human-subsidized form of food. So crops, gardens, etc. This is consistent, highly nutritious foods for them, and they're willing to make that trade-off, being in a highly lit area because it has high amounts of forage. When we actually model activity for these different levels of nightlight, on the top we have the low light group, medium light, high light. In the top two, we don't see much of a relationship in how fast they move for different levels of vegetation greenness on the x-axis. They do tend to move slightly faster, shown by this value being above 0. So 0 is the average movement rate, Anything above that is faster than average, and anything below that is slower than average. There's a little bit of relationship where when vegetation index gets really low, they tend to move faster, which makes sense. It's no longer a very good food source. Let's keep moving. We're not going to sit around here. But that relationship gets really intense in the high nightlight area. As the vegetation greenness goes down, those deer are moving really fast. They don't want to spend a lot of time there. They're hustling. And it changes once it gets really high vegetation index. They settle down, they slow down considerably, and they focus and concentrate on getting that forage off of those areas. If we look at a 24-hour clock here on the x-axis, and this is just the raw movement data. Again, classified by those 3 different levels of nightlight that those animals are exposed to. So here in blue, these are deer that have a high nightlight. During the middle of the day, they're moving slower than their counterparts. And then at night, it looks like they start moving slightly faster. So we're starting to get a little bit more evidence that's supportive of a predator shield. Somewhat, they are moving more slowly and they're concentrating in those highlight areas because it has high levels of forage measuring with vegetation index. When we model the activity pattern, which I showed you earlier, accounting for sun position and moonlight, again we see that deer in the high nightlight area are lengthening their activity period. They're not going as fast, which is indicated by those values that are above 0, which is the average movement rate. So again, this is showing that they've slowed down and they're spending more time in those areas of high vegetation. But they're mostly active in the crepuscular periods of the day, dawn and dusk, and at night. So finally, I just want to talk about some of the steps we're going to be doing in the future with this analysis. I was really hoping that we could have gotten this done and could have shown it to you all, but we didn't quite get there. But the next step is to use step selection functions with this data. And these are really cool. Essentially what they do is they calculate step length and turning angles, and they can look at the effects of different covariates on those step lengths and turning angles. And we can use actual movement characteristics from the GPS data to create random points in a much more intuitive way, I think, than resource selection functions. And as a result, we can start to infer resource selection at a very, very fine scale. Why does an animal decide to leave point A and go to point B? And what is it about point A that makes an animal move faster or slower? A diagrammatic way to look at this is if we use an integrated step selection function that can calculate both resource selection and movement. Imagine for the top panel, we can understand why that bear chose site B. What covariates, what level of light attracted that animal to select that particular spot. Well, we can also answer with these models, what was it about site A in time 1, for example, light levels, that may have influenced the movement rate of that animal to time 2. So was there something about light that made it move faster to its next time step? And we'll be using this analysis not only for the cougar and deer data set, but a growing database of other GPS-colored individuals, including elk, moose, wolf, fisher, black bears, coyotes, and hopefully others that might be out there, to see if we can see some relationships between different taxa and species to nightlight. So in conclusion, I hope I've convinced you that artificial nightlight and noise are indeed widespread forms of sensory stimuli, and some would call pollutants. But honestly, their effects on wildlife are very underappreciated and underexplored. I think it's a really exciting line of inquiry, a lot of interesting questions to ask. And I think they're important questions to ask because preliminary evidence suggests that these stimuli appear to be altering basic predator-prey interactions. And we still have to understand why, what are the mechanisms that are influencing these changes in the high nightlight area. But I do think that it has something to do with landscapes of fear. And there's a really exciting development in the literature on landscapes of fear, and I think that this contributes to that literature. I also think this work is important because the human populations continue to expand, particularly in the Southwest. An ever-growing wildland-urban interface. So these problems aren't going anywhere. They're only going to grow more intense, more severe. And there's all these attendant issues related to that expanding interface, including human-wildlife conflict. So maybe understanding the ways that Nightlife might mediate those relationships will be important for reducing conflict as well. And the exciting part of all this is that the tools and the data exist. That we have remotely sensed information, we have data on animals, and we can start to address and answer these questions. And the other part of this kind of work that I'm excited about is that, in the world of all the different threats that face ecosystems, like climate change and widespread chemical pollution, which, at least from my point of view, it starts to feel like I don't even know where to begin. It's one thing to understand what's happening, but it's one thing to figure out how you would mitigate the problem. What could you actually do? Mitigating this problem is relatively straightforward. I've asked my colleagues who are experts on this, I said, how do you handle light pollution? And they literally say, we just put shields on lights. It's as simple as that. If you can reduce stray light by putting shields on it, it would, 90% of this problem would be resolved. So it feels like this category of a problem that we can actually do something about, we can get ahead of the curve, and we can make a difference now rather than later. Thanks for your attention.
Questions?
I wonder a little bit about the kill data for cougars. Do you know if the kills were made in the daytime or the nighttime?
Good question. I don't think we know. Those kill sites were, they used the GPS locations of the cougars and the deer. So if the cougars concentrated, then they knew that there was a kill site that they would go. And I don't think they know if it was daytime or nighttime.
Let's assume that some of them are during the day. They probably are. Then it may not be light so much that's driving that pattern, but other things about cities.
Yep.
The amount of human activity and things. So I wonder if you could try to get at that a little more.
Yeah, that's a really good point because it could be an artifact, but it's not actual. Yeah, portal. It's not actual causal. I wonder. Yeah, I have to check with our colleagues to see if they have some sense of that data. Yeah.
Maybe they know for that population how much hunting is typically killing occurs at night.
Yeah, I think we're relying on the fact that cougars tend to hunt, crepuscular at nighttime, so that most of the kills are probably at night, but it's a good point. We don't know that for a fact. Thanks.
So lots of places you see deer with people where deer have almost no fear of being in that environment at all.
Yeah.
If you have the light is with people, that seems to be a challenge to sort of sort out that part of it, although you have sort of the temporal aspect of the data.
Yeah.
What about hunting? Human hunting.
Yeah.
Do you see any differences during the seasons and sort of lag effects of what the deer are doing and how they might move or shift their behavior in relation to that?
Yeah. That's a great question, and there's two parts to it. On the hunting part, some of the sites definitely have hunting, and I think we have to parse that out. And the next step we're doing is to break it up into season, so that we can isolate the hunting season from everything else. Isolating the collinear relationship potentially of light and human presence. The way we're trying to get at that is what I didn't show is that we've accounted for other human infrastructural factors like housing density, road density, distance to road, to try to parse out whether it's infrastructure or light. We don't know human presence in the sense of actual numbers of people that might be utilizing an area. But I do think that we're catching a signal of light independent from those other infrastructure. The hunting is a really good question. And I think, so for Salt Lake, the area that we have, they can't hunt in that area. In Reno and Flagstaff, I don't think that there are game management areas right next to the city. But some of the really dark areas, I'm willing to bet that some of those are definitely in game management areas. So we want to pull that out a little bit, because that would add to the predation risk calculus for both species.
Yeah, I guess I was thinking along the similar lines of just the difficulty of teasing apart the light effects from all the other anthropogenic effects that are probably highly collinear with it. Are there areas that are bright with artificial light that are relatively more natural with less habitat modification or human development, where you could try, or I'm just wondering, even putting in those other layers, I would imagine they might be so correlated that it wouldn't be valid to include them both in the same model, because if they're too highly correlated, but maybe some targeted comparisons.
Yeah, so we're really A, concerned, and B, focused on trying to figure out how to parse that out. Our concern doesn't feel like it's as bad as we worried about, particularly with the collinearity question. It's surprisingly not collinear, not even somewhat. Light seems to be very different from the other human-related factors. I think part of it is because it can spread out. And so the sensor is picking up a lot of sky glow and dispersing light, and so then you don't get the correlation to the present, like the exact location of the road or exact location of the housing units. So for like Flagstaff, some of those medium-sized cities, I actually think that a lot of light is not correlated to the physical location of infrastructure at all, because the actual footprint of those study sites for the physical infrastructure is really quite small. Actual cities and roads, when you draw the boundary box, it's really tight in the middle, but the light has a dome that goes way out. So I still think it's natural. A lot of the area is very natural. They're exposed to that light coming from the city. So I think we are capturing that interface of where it's essentially a natural area, but the light is contributing to their sensory environment. I'm hopeful that the step selection functions will provide us a little bit more information on where they left and where they go to, and we might be able to have a stronger case that light has something to do with it when we control for roads and business. Yeah, it's going to be a struggle to make the case. Also, because the light is at 750 meter resolution, you don't have pinpoint GPS location of this light pole, and you can watch an animal kind of move around it. We're making an assumption that that pixel means something to where an animal goes. Yeah, thanks.
Did you look at differences between the two deer species? I'm assuming there is both mule and white-tailed deer.
These are all mule deer.
Oh,
Yeah. But yeah, that'd be a good point. They definitely would behave potentially very differently.
I have a question about recreation. So I'm working with the Forest Service right now, and I'm working with some wildlife managers who are really concerned about nighttime recreation, headlamps, biking, night biking. I was wondering what you think some of your implications are for that kind of small temporal scale, not a big city with constant lights at night, but more of a short term that can be somewhat constant.
Yeah, I have a couple thoughts. It's a really interesting point. And in a place like the Southwest, where the outdoor recreation is clearly a really popular activity to be involved in, I definitely think that it could have an effect, because it would be a very novel stimulus, an extremely dark background to have this, concentrated point source of light that's moving. It's unpredictable. My feeling from the literature is that wildlife can habituate to disturbances, even fairly intense disturbances, if they have very predictable paths and routes. So if you have a light, like a headlamp, at least for me, I do a lot of this, wherever I'm going, that could be very unpredictable, potentially affect where an animal is going. It could disrupt their hunting. I've been interested in trying to compile some data on that from Strava, for example, to see if you could pull together relatively big data from existing apps that collect, people who have this app and record their locations. Maybe you could get at that somehow. You could start to say, over 6 months, 500 people recorded publicly their locations on these trails, and you can purchase that data from Strava and see if there's some relationship with that. You don't know if it's, I'm not sure if you can know if it's at night or not, but it could be a rough proxy.
Kind of a follow-up to that. What do you think about if this nighttime activity is happening in, I noticed you have like at least one national park in your area, and there's other national parks that you're going to be incorporating this into, where wildlife around those areas might understand those spaces as like non-threat areas because they can't be hunted there by people, or like they're just used to being around more people in these relatively dark areas. I don't know if that's a factor or not, but.
Yeah, so working with the Park Service, they're actually really concerned about this, and especially at parks that are, the visitation rates at parks has really grown in the last few years, which is great in many respects, but in terms of these disturbances, they're really concerned about. And to accommodate a lot of those visitors, they're building new visitor centers, larger parking areas, heavy use of lights, because there is what I understand is a unproven related thought that more light makes it more safe. I guess the data doesn't bear out that way. But there's put more lights in because people will feel more safe, particularly in a really dark national park. So you can imagine that there are these little domes of light and there's probably this buffered effect around those parking lots that are much larger than we think that they are. And I don't think anyone really has a good sense of that yet. But the parks do record the geo-reference location of their lighting fixtures. So you could, one of the things we've started to do is to correlate the exact locations of those lights with the satellite data to see if the satellite can pick up, even a handful of those light fixtures in otherwise extremely dark background. And it does. We have that for Yellowstone, for example, and we can see, I should have put it in there, but you can see the parking lots in the pixel brightness from the satellite imagery. So there could be a really interesting way to connect those and start to ask questions at scale for across a really large national park or multiple national parks.
I'm curious how the kind of in that, so kind of in the bubble around these light fixtures and the amount of light, or let's say you've got Salt Lake City, you've got the giant bubble around Salt Lake City, how that amount of light not directly tied to the infrastructure that's scattered kind of compares to the light of the full moon at the peak of the lunar cycle. Because I know, at least from a natural history perspective, and I think to me borne out in the science, there's a link between predator activity and the amount of light from the moon, especially if you have fresh snow on the ground that's reflecting it.
That's a great question. And I don't have a very good answer for it. Because my colleagues on the grant, actually, we've talked about this a number of times, and that's part of the reason we try to account for moonlight in the activity analysis. And I'm trying to remember the numbers, but a full moon generates a lot of light, and it's unclear to what extent artificial light interacts with that moonlight. It's unclear how animals can discern artificial light from natural moonlight. And as light fixtures move from yellow sodium to more LED blue light, is that another factor that's involved in how animals discern those differences? And I don't know. I think it's a very valid question. Does it all kind of go out in the wash? Like a really, moon isn't full moon and that little bit of light isn't even registering, versus a new moon, in which case that light really starts to play a larger effect. But it's a good follow-up. You figure out the actual lumens, compare the total levels. Yes, sir.
Are there on-the-ground sensors of light that exist, or a sensor network that measures light on the ground ranges? Just trying
Yes.
to compare downscale like that, so I don't know.
Yes, there are, and there are basically really cheap meters, sky quality meters that astronomers use often just as like they want to take a reading of the sky to decide if they're going to look at the stars that night. $100, it does okay, it gives you a single reading. If you really want to do it really very well, have very fine scale readings, and ideally have more of the spectra, the cost goes from $100 to like $2,000 per unit. And I know this because I explored it for a number of weeks because we had an idea. So there are tools that are out there to do it. Those are used for professional grade commercial lighting indoors. They're using that to get a sense of like, what is the warmness and the spectra of light when they're building a new house, for example. So it's possible to do. It'd be interesting if we can get enough of those units to be able to do it. It's like the cheap sky quality meters aren't quite good enough to do it because they don't calibrate very well. You don't know the zero. If you have 2 units, it's not entirely clear that 0 is exactly the same for both units, so that becomes a problem. Otherwise, it's a little more costly, but it's possible. Well, thanks.
Thank you.